All right. Good morning, everyone. Well, it depends on where you are. I want to welcome you to the EchoLabs webinar on hyperspectral imaging. Dean Riley and I will be your presenters. Warren Genick here will quickly go over the housekeeping and we'll get started. We want to keep this to an hour as I'm sure you all have busy days. So Warren, could you please go ahead?
Okay, yeah, thanks for joining us today. So we will be recording the webinar and it'll be made available later this week for any who are unable to attend today, or if you want to review it again in a little more detail later. We're going to ask that you remain muted during the presentation, and we will have time for questions at the end. During the webinar, if you want to post any questions that you might have in the chat area, Scott and I will attempt to answer them while Dean's chatting with everyone. And if we can't answer it or we don't get to them all, we'll make sure that we go through them at the Q&A portion at the end. Once our webinar is completed, we'll be happy to set up some one-on-one meetings with everyone or anybody who's interested to discuss in more detail one-on-one and how we might be able to use this kind of stuff in your project. Okay, go ahead, Scott.
Thank you, Warren. So I'm going to be very brief before I hand this over to Dean. So a little bit about us. So EchoLabs was founded by some of the most experienced UAV operators and hyperspectral geologists in the world, with our goal to offer an end-to-end solution. You could see some pictures of our operations here and a little about our experience. Our process here takes total control and ownership from consultation, site survey, initial data collection, with in-field quality checks to processing and final delivery. And I know I'm ripping through the slides very quickly. We want to get to the good stuff with Dean's. So this is meant to be a tech presentation, not a sales pitch. So if you are interested in hyperspectral imaging for your property or project after this, we can organize a follow-up meeting. We'll also link our booking system, which will show up in the chat, which you can use to outline your project, upload shape files, KML, KMZs, and we'll work together on getting you a proposal. All of the data that you see here is presented in PowerPoint form via the images. However, these are all made available to our clients through our proprietary data portal that could be interacted with dynamically, as you can see on this short video. These can also be exported to your data management software. So again, this will all be made available to you to see after. It shows you how we have our data layers presented. On that note, I'm going to pass it on to Dean, and I wanted to pass this on to Dean, and you can go ahead.
Thank you, Scott. So real quick, we'll cover some background on hyperspectral imaging in order to make sure everybody has at least a common understanding, because I don't expect everybody to be experts in the field and maybe some people are new. So as you read this slide, you can see that hyperspectral imaging, or imaging spectroscopy, as it's also known as, is a way to image the Earth with hundreds of contiguous channels across multiple wavelengths. And in our particular case, we measure, and we're going to focus on the visible through near infrared to the shortwave infrared, because that's where our sensor operates. However, we are familiar and are ready to move forward when sensor producers produce a midwave or a long wave infrared. We do have experience in processing those wavelength regions for geological and mineralogical. Real quick, we'll cover Cuprite, and then we'll also cover Hope, British Columbia. This introduction is with regards to our current capabilities. You can see here, we fly RGB imagery at 3 centimeters ground distance. That's our typical collection parameters. We produce a digital surface model. We need that for topographic corrections. And then we also fly a visible and near infrared and shortwave infrared hyperspectral instrument. In this case, we have 493 channels. We have about a 5 nanometers channel spacing, especially in the shortwave infrared, which is where most minerals have their absorption features. And then we do have the 3.1 nanometer capability in the visible and near infrared. And that's important for vegetation studies, or if you actually wanted to an attempt on geobotanical, because if your area is heavily forested, which we will see later on that Hope is, we could attempt to do geobotanical studies to help you identify your deposit or effects from environmental conditions on the vegetation around, because this data is capable of that. So in 2019, we did our first collection over Atlin in British Columbia, and you can see what we collected there. In February of 2020, we flew Cooperite, Nevada, and then in July and September, we flew Hope, British Columbia. And actually, most of the data that we collected over Hope was in the September timeframe. And as you move north in northern latitudes, you have to worry about sun angle. However, we do understand where that fits within the collection schema, and so that's where we go there. Real quick, this is slides to help you with a comparative understanding between UAS, hyperspectral remote sensing, and things that you may be familiar with, such as a ground spectrometer, such as an ASD or TerraSpec, or if you've used satellite remote sensing, WorldView 3 or Aster data, or if you've had in other aspects properties with aircraft. What is also to note is our sensor can fit on a helicopter. We have not done that operation yet, but you can see the variance here, and where helicopter does fit is a transition from UAS up to satellites. To help everybody understand some of the basic physics, this is an overview of where reflected sunlight, and that's what our sensor currently works with. Whereas things in the future, mid-wave, long-wave infrared sensors, that's the red line, they work in the thermal and different wavelength ranges. But really, the important piece is the phenomena is familiar. It's been long studied in spectroscopy and minerals for a long time. And then you can see the physics and that goes across in each wavelength range. The difference in the complex versus simpler phenomena have to actually do with minerals. In much of the case, from the visible through near infrared to the shortwave, that phenomena interacts in a nonlinear fashion. It does start to approach linear at about 2000 nanometers, and it behaves in a linear fashion in the long wave infrared. However, atmospheric compensation behaves the inverse. So atmospheric comp in the visible to shortwave is linear, and it's nonlinear in the long wave. So this is just a summary slide to help you understand where we're working. Next slide. This also to help you visualize how this works with a UAV and what aspects of the collection. And so it's just a real simple of how the reflection goes or emittance of the material with temperature contrasts work. And it's just a real simple cartoon of how the sensor would work in collecting data. Next. Our sensor is a push broom scanner. And in this case, we use the forward motion of the aircraft to collect the lines. That's the scan direction. That's somewhere between 2,000 and 6,000 lines. Sometimes if you get over 6,000, and we've collected up to, I think, 18,000 lines, it does get unwieldy for the processing in on that backside. However, it is extremely manageable and can be done. We are 620 pixels wide. So when we fly at 180 meters above the ground, we're typically about 62 meters across, to give you an idea. And the wavelength range, and that you see it on the right-hand side of the image, it's to help you understand that they're just stacked like along the way. So if you think about it from the aspect that most of us, unless you're colorblind, see red, green, blue. We have a red eye, or we see red, we see green, and we can see blue. And you can have images, and cameras will produce grayscale images in each of those. We get to be able to do 493 channels in this case. Next. And to help you with the phenomena and minerals that are identifiable in each of the regions, the visible to shortwave infrared, you can see here, Things that are most important geologically, if you're doing exploration or mining, or even environmental assessments, are the iron oxides. You get phyllosilicates, so the clays. You have the sulfates, muscovite, chlorite. We also can detect in the rare earth element oxides. They have very distinct features, really in the visible to the near infrared. So from about 500 nanometers to 1,000, and they're super distinctive, especially and do not require large volumes. So you can detect the rare earths in minerals like apatite or monazite. And then it's not necessarily the focus, but it's important to note that we can detect vegetation, water, and snow because we detect those to mask them where they're going to obscure the minerals so we can highlight your processing. And then the long wave infrared is here for helpful understanding. So one of the things that we look at and how we look at working this on a processing aspect is there needs to be a mineral or a rock spectral library. And we start with the publicly available libraries unless you have a spectral library that you want to provide that's from on site. This is just to let you know that they are freely available and where they exist and generally the wavelength ranges that they cover. And then on the lower right, you kind of see a graphic that highlights working from this general set unknown, very exemplar, but they may or not going to be site specific libraries, such as like the USGS or Aster library, to where if you have people collecting ground spectra doing on-site exploration or in the mining site, you can use ASD spectral evolution, or if you have any of the other instruments that are out there. The third way, and this takes a lot more time, but it is arguably one of the most efficient ways, is to actually, if you know the locations of a particular mineral suite or rock suite that you're interested in, we can extract the in-scene spectra and then run it back through the data to process. And the reason that's important is that spectra is the same, has all the same characteristics for normalization as the data was collected in. So there's not any potential errors, or the errors are minimized through that process. And that's why in-scene is there on the right. To help you understand how we view our processing chain, which is a little different than airborne and satellite, and it's really most notable if you follow a UAS and nadir and you go across, it's step 3 where the orthoreferencing is third and then conversion to reflectance is fourth. In most satellite and airborne imaging, hyperspectral or multispectral, that conversion to reflectance usually takes place third. But because we're flying so close to the ground, we actually need to ortho and georeference first, so we get all the right corrections going, and then we can convert to reflectance, and then we use that DSM that I spoke of earlier to do topographic correction. The reason off-nadir UAS operations and ground-based off-nadir operations are listed as well is because those are areas that we know we are migrating our production path into for collection and then to produce product. And you can see really that they follow the same process as at a high level. There is some challenges in the details because you're now, instead of flying above the target, you're flying 90 degrees or stationary 90 degrees to the area like a bench. So, but it is to follow the same kind of process. Next. And this is an overview of our sensor, which is a Hyperspectral Molnier sensor. And it operates as 2 independent sensors, but they are co-aligned. And so you have the visible, which is the V1240 and the S620. And you can see they can be, we can collect independently those, and we could process them separately. However, for where we see the benefit in mineral exploration studies and environmental studies and open pit mining is actually to combine it, is the VS620 from Hyperspecs, and you can see the pieces there. What's really important to note on the 620 is that it's got a signal to noise ratio of over 900, And most airborne scanners, some of the newer ones are starting to approach that same signal to noise ratio, but that's the airborne, so they're a much bigger instrument. We have probably one of the best signal noise ratios on the market with the 900 in the shortwave, and that's really critical for mineral detection. This is a slide that I've built over the years to help understand how all of us or most of us should understand how we want to solve the problem. You have a mining objective. It can be an environmental aspect for remediation or monitoring. It can be exploration, or it can be in-pit operations. Generally from that, you've got some deposit model that you've already worked up, formed up how you want to work. From there, the minerals that are part of that deposit model, whether they're things that alter out from the leaching process or they were part of the hydrothermal alteration, they determine the observable phenomena. As we work through it, we can, and the reason detectable phenomena is because there are environmental constraints that affect that. Now, if everything was all things sane, we wouldn't have data costs or constraints. Well, cost is one of those things. What resolution do you need? Maybe you're doing a full regional survey and you can handle 10 meter or 30 meter data to solve your problem at the stage you're at. However, if you're coming to us, you're worried about having a high fidelity models. So the scale that we're working at is we can image as low as typically in the hyperspectral 5 centimeters up to a meter. And then so that helps guide your data selection and what you need. There's an image processing, analysis, interpretation. You produce a thematic image or a map. You want to integrate that and model it and put it into something like Vulkan or Leapfrog. But those data that we can also fly and collect they're outlined in black is aerial photography, imagery, and topography. We do that already, but we've also know we can fly magnetometers, VLFs on a UAS system to do that to help satisfy your mining objective. So we're moving on to cuprite. So why cuprite, especially across the board? Cuprite's a quintessential, it's the case example since the 70s for remote sensing, for satellites, for airborne, people test out there. It's an epithermal high sulfidation deposit. It is barren, at least to my knowledge. People do tentatively put tenements down or will mark out where they think they want to explore. However, nothing has come to fruition in over 30 years. There is also some interesting minerals that have shown up out of cuprite that then they've found later on in other deposits worldwide, such as buntingtonite, which is an ammonium feldspar. And so you can detect the ammonium features in the shortwave infrared. And then, so really quick, the deposit, it's Cambrian metasediments. You've got phyllites, quartzites, some limestones. Those are primarily, if you look at the graphic on the right, they're on the left, they're in the blue and the orange and the yellow. The tertiary conglomerates are over on the right-hand side. They're in the browns and the pinks. And the intrusive rocks, which are the quartz latite and cyanomonzonite, are on the left side, but we won't be focused on our area where we're at. And really for cuprite, you can see all the minerals that are listed that are kind of always there, and typical high sulfidation epithermal deposit. And we'll have some later on examples covering opal, alunite, and jarosite. So these two figures are really to help you further understand the alteration system and some gross level geology. And you can see that on the left, the gross level geology, talking about the tertiary elements. And then on the right-hand side, you can see where it's heavily silicified alteration. You've got opalized alteration and then the argillic alteration as well. And so this set of graphics comes from Patrick Swayze et al. And they float Avarice. If you're familiar with that, that is probably it's now been surpassed in the visible shortwave by Avarice NG. and Jet Propulsion Laboratory flies it, but it is arguably the best instrument in the world. And the USGS has mapped this before, but the highlight piece is the overview on the left in the white box, and then on the right hand side, the white box, we're going to go in and focus in on that greater detail, but you can see the red line, and as we got the white transect that's on this left graphic here, and you can see the alteration minerals in the legend on the right. Right in that blow up above the legend is where we're really going to focus in that scaling. You can see alunite, specifically a potassium alunite. You see a little bit of kaolinite, a little bit of opal in there in that mix. And then that's what we're going to show here in a second, our imagery that we've flown over. However, I want to cover spectral signatures so everybody's familiar with this to begin with. And here's the alunite spectra, and you can see that they have features at really a broad bottom at 2165. There's a small peak at about 2188 to 2200, and then it has a second absorption feature right about 2320. And then the white mica, so this is muscovite, illite, paragonite, phengite, things of those groupings. So you're looking at the micas and some other similar things. They all typically have a feature at 2200 nanometers, and that wavelength, and you can see that right around the 2200 line. This position varies, and it varies with sodium and potassium content. And that can be an important indicator for in your deposit, especially for porphyry copper and epithermal systems. Next slide. And then so kaolinite, which actually has a very nice doublet, and its polymorphs, which are halloysite and dicite. The well-ordered kaolinite has a and you see the first absorption feature, it's about 2188, and that feature, how well it's characterized, tells us whether it's well-ordered or disordered. So you can figure out whether it's something that's from hydrothermal systems, or is it a product of retrograde alterations or weathering processes. And dicite and halloysite both follow that as well, but it has a nice doublet that's very distinctive and easily for mapping. This is hydrosilica, so we're talking opal and chalcedony. It has a broad feature at about 2250, and it's kind of undistinctive, but it does have a broad feature that can be mapped. And so we'll go to the next. Jarosite, and this is just one aspect of jarosite's actually got some really nice, unique features, not just in the shortwave infrared that we're showing here, but you can see it sitting right around 2250 because that's the iron aspect that's in the jarosite. It does have features in the visible because of the iron. It also does have some stuff that's in the 15 to 1700 region as well, because sulfur maps out there, and that you can start to also map the chemistry of the jarosites and some of the sulfates in the 1500 nanometer region. Next, chlorite, and that's just because chlorite's commonly, with the propylitic alteration is there, and it's something that we, especially in epithermal systems or porphyry systems, we pay attention to. And it has the FeO8 feature is at 2250, and that's the first line that's dotted through. And then the 2320 is the typical chlorite, which is where more the magnesium feature is. And since chlorite does adjust with chemistry, the iron in that 2320 positional shift and the 2250 positional shift based on the iron magnesium content. We can go to the next. So this is an overview of our RGB and DSM from Cuprite, and that you're looking at a 3 centimeter pixel on the left and how detailed that can be. And then the digital surface model that was produced is at, this one was at 50 centimeters. However, we can go down to 3 to 5 centimeters if that's your request. And so it's just really to highlight that the amount of detail you can get out of the topography with our data. And this is from the EVs. Onto the HSI instruments. So just so everybody's understanding, there's a true color composite on the left and a false color composite on the right. And the wavelengths that they're are slotted in the red channel, the green channel, and the blue channel are what's in parentheses. So for example, the true color composites sit in red at 650 nanometers, green's at 550, blue is at 450, and it looks, you know, like a traditional color or what you would see with your eyes if you're above the area. And you can see the multiple flight lines that have been flown. And then on the right, because it's shifted into false colors, so we move the red out into the almost the near infrared at 750. So it's beyond red there, what typically people see. And you can see some coloration differences in different spots, but that's what that is to help you with your eye interpretation. This is just to give you an idea of what the georeference true color is. And so the outer markings are every 100 meters, and you can on the grid lines, and they're very faint within there, so it didn't obscure the whole image, is blocking it every 100 nanometers. And it's just to show you that it's map quality for your, whether you use ArcGIS, Map Info, or some other GIS product that you can use it with. One of the things that in the initial stages that I like to do is to develop some false color composites and then run them with a decorrelation stretch, choosing particular wavelengths to focus on features. So like I spoke about earlier with the white micas, so 2200 nanometers is an area to into 2330 are two areas, hey, we interested in because of white mica and chlorites and things of that nature. And the 1650 is where's a sulfate feature, it maps. And the reason to do the decorrelation stretch with it, which is basically it reorganizes the data. When you look at the left, you can see kind of some stuff there in that false color composite. You see the purples and some greens, and you're like, okay, that kind of makes sense. When you flip over and apply the simple transform to the data, things become really stand out to you. And that is, you can see the area that's in reds, to see the cyans, and those things distinctly come out and help you from an image interpretation perspective, provide more insight into the data. And then this is a same thing with a different set of wavelengths. So we changed it from really the blue, changed over instead of 1650 to 2165, and you can see the differences. And that 2165 feature is really where alunite sits. So where you can kind of see it is the brown on the left, it really comes out and is distinctive on the right hand side, and it's just a simple transform to help with image interpretation. And the yellow green area really is highlighting the opal areas, and that's kind of in part because of the way it sits. So to highlight with alunite, and we saw it a little bit in the base image interpretation, we applied a unmixing process here with alunite as one of the end members supplied into the unmixing algorithm. And you can see the grayscale image on the left. And we're focusing on the upper 10 lines in this case, because when we flew Cuprite, we actually focused on operational first and say, could we collect 100 hectares or a square kilometer, and not worrying about the sun angles. And in this case, the upper 10 lines are above 30-degree sun angles, so they're better for mineralogical and geological processing. And 30 degrees is typically the cutoff that we want to use. So that's where we stuck to, even though you saw in the false colors and some of the others, much bigger extent. It also makes it easier for interpretation when you focus in on maybe this upper half. So you can really see the potassium alunite in red, and that's a higher quantity volumetrically. Since we're using an unmixing process, we can get an abundance. And we can go to the next slide. And then jarosite, and you can see in the grayscale that there's the dark area, and that's like, okay, that's not jarosite. And then something bright, and you can kind of see some areas here and there, but it really shows up well when you put it into the rainbow image on the right, and see the coloration to it, and you put a small thresholding. In this case, the thresholding is like less than 10%. Everything is black. So that's where it just highlights the areas that have a large amount of jarosite. Next slide. Kaolinite, we mapped that as well because it is prevalent in cuprite, and you can see what's interesting and notable in the kaolinite, and you can see it up in the, if you haven't caught it already, I will highlight up in the upper left corner, from the USGS publication, a highlight of the transect area that they flew and did. But what's notable to see is the level of detail here that you're actually getting. So just the frame of reference to help you. And then on the far left, you can see kaolinite is there as well, but the alunite is not showing up in this because we used a kaolinite unmixing, and it's showing up outside of where we had previously seen alunite or jarosite. Next. And then opal, because that opal and jarosite actually in this area are mixed, and it just takes a little bit of iron oxide coating the opal. And you'll see that especially right there on the right-hand side. And you can also see the little bit of the opal showing up where the kaolinite previously was. So, but these layers that are produced are easily ingestible into your GIS because they are geo-referenced already. So you can develop with your other data that you have for your exploration or mining projects, put them all together. One of the things that I find useful and this is a little older school in processing, is to take those unmixing images and place each one of them into a respective color gun. In this case, we put alunite, jarosite, and kaolinite into the red, green, and blue color guns. That's on the left. And on the right-hand side, we put opal, jarosite, and kaolinite. And then what happens is when you mix red and green, you kind of get some yellows. When you get red and blue mixed, you get magentas and purples. And when you mix blue and green, you get cyans and colors of that nature. So it helps you work and identify what couple minerals may be coexisting in the same locations because the colors, or they're singular. In the case of, you look on the left, the alunite shows up really well. It's bright red, and there's pretty much nothing else there. And on the right, you can kind of see that area is devoid. It's blue, dark purple, blue at best to black. And on the right, and that's the area would be devoid of alunite because it's dominantly that anyways. And you can see the other purples, which are the opal and kaolinites coexisting because that's the purples and magentas. And then areas that are white are areas where kind of all three exist. Next. And this is to highlight, it was an early on study, and we needed to go back and run the other ones, which we'll see here later, is the additional wavelength mapping. So and cuprite really hasn't been wavelength mapped in the essence of how does the minimum absorption feature change within a pixel? Where is it changing across the schema? Because it allows you to potentially see how fluid flow is working, especially if you're using for white micas. So we focused on the ALOH region, which is for white micas, and we mapped out the minimum. The longer wavelengths tend to be in red, the shorter wavelengths are in blue, and that's what we're seeing here. In this case, the big line of distinction, because that kind of catches everybody's eye between the red and the black, is actually where we think it's what's called bidirectional reflectance problem between the collection days. And so what we want to go back and do is fix that to see if we can correct it out. And we're working with an atmospheric software provider to help us with that, because that's a distinct problem in the UAS world that we're going to have to be distinctly aware of. So we're already working on the cutting edge solution to make sure that we handle the BRDF, but that's what we're pretty sure is going on there. But for the rest of it, and now we'll move to Hope is a porphyry copper deposit in southern British Columbia. Copper is the primary, silver is the secondary. You can see that right up on the deposit geology. The most interesting thing in porphyry deposits in British Columbia, and why to look at Hope comparatively to other ones, is Hope has tourmaline breccias associated with it, and tourmaline is not commonly associated with the rest of the porphyry copper in Hope, but tourmalines are fairly common in the South American porphyries. So working with Imperial, and I'd like to thank Bill Fisher for helping with this, and we went iteratively through the process. And he supplied some stuff later on, which I'll share. It was exceedingly helpful, and we will gladly work with people to develop unique products, such you'll see here in a little bit, that are tourmaline focused. You've kind of seen this same type of thing, but it's to highlight the RGB and the amount of RGB image on the left, which shows you how vegetated the area is. There's snow up on the higher peaks, and then a correlative 50 centimeter DSM. But you can see bare earth spots. And if you had satellite or coarse airborne data, you may not have the number of pixels that you would have to identify the rocks underneath in those bare earth spots. Next. So this is a little redundant from what we saw earlier in regards to the chlorite and the white mica and slides on spectra. But really you want to focus on, and we do have a follow-on piece with the tourmaline, but the tourmaline is in this region of 2000 to 2500 nanometers. You can see 4 to 5 features. Elbite has a feature that's below 2200 nanometers, right around 2185 or so, 2160. But the other features are Elbite in whether it's dravite or a schorl, are all at 2200, 2250, 2300, 2305, and then another set that actually varies, and we'll see that in greater detail at the next slide. Or actually after this processing, but we'll get to it in a second. So the processing methodology that we used for HOPE is the following, and you can read it here, and why we chose to do what we and how we applied it. Just so everybody's familiar, because quartz is fairly common in epithermal systems and porphyry systems. Quartz doesn't have a visible near infrared signature. It's more or less flat. It's very bright, but we do look for it just to make sure we're not, because sometimes you get a little water feature in there and things like that. And we really didn't focus on the iron oxide or chlorites for interpretation or processing, as our partner in this with Imperial was really focused on helping and try to solve what can tourmaline tell them. We can go to the next. So the reason tourmaline was especially important at HOPE is from Bill's work here, and you can see this in the overview picture of Elbite, dravite, and schorl. Is like before, we've got the multiple features, but really at about 2350 or so to 23 to 2400, you can see the feature change. So the line that's 2350, you can see that magnesium content and iron content change between dravite and schorl. It does change with Elbite way out farther, but you can make other spots to help distinguish Elbite from dravite and schorl, such as the below the 2200 or right around 2300, it changes around. So we're going to really focus on the dravite schorl issue. And what was noticeable in Bill's ground data is you can see inside the breccia pipe, which is where the ore is, or the higher copper content, and then outside the breccia in the blue dots. And there's a very distinct separation between the two. And so if you look at the x-axis with the FeOH, you see that, okay, but it's correlated with the magnesium content on the y-axis. There is a negative correlation somewhere between like 2365 to 2250. You could run a line through there, but that's important so we could try to help map out those two areas. So later on, and we'll cover the iron FeOH mapping. That's why we produced a wavelength map for him in iron and in the magnesium in these regions. Next. And this is to highlight on the left is an unthresholded mapping from 2185 to 2200 nanometers. And this is where tourmaline sits in white mica, and you can see the bright spots or the bright wavelengths are sitting around 2200. And then and it has a lot of not a lot of bends. And on the right, we have it bend into 5 nanometer groups. And you can see that on the right. Depending on what type of product you're looking for and interested in. And you can see a distribution in here with the FeOH feature, and we focused very narrowly for 2240 to 2265, and the variances that go on with this, and just to highlight the differences. And you can see that a lot of the FEOH stuff, that how depending on how you want to break it in, is beyond 2254, 2255. And then, so this is the first magnesium feature. So this is right around 2300 nanometers, and really to focus on. So what this is telling us is actually that a lot of what we're seeing in this region is actually probably closer to chloride. The chloride's also, because we know it's in the system, that we're probably seeing a fair amount of chloride, and it's overprinting the tourmaline, so it's kind of masking the tourmaline signature, which when we saw this, we needed to force into the next slide and really focusing and trying to map the longer wavelengths, like we saw from the ground data that Bill was collecting, and seeing a distinction between the 2350 to 2380 range for magnesium for the tourmaline, and mapping that wavelength. And you can see there's a lot greater variability in this mapping, but it also has areas that are things that are going to be within the pipe, which is the 2380, 2375 area. And we know that from Bill's ground data, but you can see how they map in well, and the differences in the different products there. Next. But also to help you with familiarity, that we just didn't focus on that. Do we help Bill in Imperial with using some of the more traditional in the color guns? So we process tourmaline using matching. We process chlorite and put white mica. And so we put chlorite in the green color gun, and white mica, so the illites muscovite in the blue, and tourmaline in the red. And it was on the non-thresholded image on the left, you can kind of see the nice gradation. It's got good areas. But when you do threshold it based off of the value that was returned, and this is a little bit of the art form, but fortunately we use correlation as our mapping preference. It does allow us to say, hey, we can stick to 0.5 or above, or 0.8 or something, fairly quantitative. And it highlights the areas in magenta, which shows where things are tourmaline and white mica together. Next. And then the white mica, just to give you help, because the white mica on its own, it shows you what it looks like without a threshold. Because we know there are iron oxides and some of the other things in the area, just we wanted to see what the iron oxide would look like. And this is in the case of goethite. And so goethite's in the red on the left, the red color gun, chlorite and white mica. And all we did is swap that out versus tourmaline, because it's the other mineral that's fairly ubiquitous in the area. And then you look at it when we threshold it, and it's really showing up as the white mica areas in blue, and to help. And then one of the things that can be done is that we can really go in and focus and help you with, if you have specific lines or specific areas of interest. And what this is showing is to help you with the mineral and us with mineral identification. If there's known locations, we'll focus in on it. So we have a true color here on the left. We overlaid the white mica areas on top of it that were run through, and you can see that migrate through. And then we highlighted tourmaline, and it's really, and I think we've got another slide here after this. So what you can do is then pull the spectra from it and really examine the features that are important in here. And this is to help us further make sure that, one, the mapping is going correctly in going through this, but we can also say, oh, are we missing something, or are we picking it up? And so we can see the iron oxide features, which are what's listed at the 550, 500 or so, 650 and 950. And then you got smaller features. And then we can really see the areas where white mica and chlorite and everything's kind of mixed in the shortwave infrared, and they're highlighted in the lower right graphic. And you can see that the feature, and this is probably a little bit of a mixture of really chlorite and white mica, but there are some features that are out beyond, and it's not 2450, and it's just below that, so that it's a mixture of probably white mica, tourmaline, and chlorite there. We can go to the next one. And this one is even a little more distinctive, and you can see where that feature in the, not the 2200, because that's really where tourmaline should be fixing. White mica will vary in there, but tourmaline sits right around 2200, 2205. It doesn't vary too much on that feature there, but we can see some variance in the 2350 range going on, but we're still mapping the same type of things. And it also, in this case, if we go back for a second, you get to see, and this is, the data is really good spectrally. It's not, because we still have some small atmospheric effects, but really not many. So it's looking really close to, like, if you're used to an ASD or a TerraSpec or Spectral Evolution handheld, and you're using that for ground measurements, this spectra looks very similar to that. And this is just to help further highlight some areas where what the true color when we map through in an additional area, and to highlight the areas that were kind of devoid. You can see where white mica is dominant, but then there's some areas that are really tourmaline. And this is an early on process, and I built a snow mask later on, because this area that's in red on the tourmaline, that in green, you can see it kind of in the right hand side, it's snow. So I had not had to build a snow mask before, because I typically worked other areas, but we built a snow mask for it for later on processing. Next. And this is just more of the same of highlighting the spectral analysis and what we can really pull out. And you can really see on the lower right, beyond the OH feature that shows up at 1450 in that doublet there, but is the amount of features that are visible within this spectra, and each of those significant. So what this one especially is telling us is that we have tourmaline, we have chlorite, we have white mica, and it's all mixed together. And this is more of the same. Lastly, I'd like to thank you all for attendance of our webinar, and now we can go on to questions. Scott?
Yeah, thank you, Dean. And one thing I really wanted to mention, this I should have said this right at the start, was all of this data, other than some of the satellite and man data you saw, was ours. This is real world data collected as it would be for any commercial operation. So it's all of ours collected for our own R&D or for our clients with permission to share with you. Yeah, now for the Q&A. So if you would like to, a couple of people asked questions in the chat, which we were answering there. But if anybody would like to ask a question, I believe you can request.
Yeah, you're now
unmuted.
welcome to raise your hand or unmute yourself and ask away. Or you can post it in chat too if you wish. Some of the questions that we did have before was just confirming that the sensor we do use is, yes, the High-Specs Mjolnir VS620, the combined sensor. That's for the hyperspectral. But as you've seen, one of our key things is that we also make extensive use of other supplementary sensors. So RGB, high resolution RGB, RTK quality survey grade topography. And then we have capability for LiDAR thermal mapping. And in some cases, or in future cases, we will have VLF and MAG available as well. Flavia asks here, or do we have any geophysical tools?
So Flavio, I'll try to answer it the best I can. So my guess is you're asking about magnetics or VLF. That's going to be in the future. The thing to note and is hyperspectral remote sensing is a geophysical tool as well, because we are measuring the radiance of the ground and the reflection. So it's, but I think you're actually talking about magnetics or VLF, or EM, and we do have discussions about buying our own, or we can fly them though, if that's important to you.
One of the things with that is we've been focusing on hyperspectral because most of the challenges there are challenges in the operations, but also on the processing. And while we don't want to downplay the amount of work that's obviously included VLF, MAG-EM, it's much more straightforward. Dean, you can correct me if I'm wrong, than the hyperspectral imaging would be.
Yeah, yes, you're correct, Scott. And it's also, we can fly, where we've looked at it operationally is flying outside the sun window, which is typically 10 to 2 local, is being able to fly the geophysical tools on either side, including a LiDAR on either side of that window to increase our own efficiencies, but as to helping with the process anyways.
Fantastic. And yeah, we'll keep this open here for a couple more minutes if anybody has any questions. Oh, sorry, here, Lori asked a question.
Yeah, Lori asks about the specs on the flight plan, payload of the sensor, length of flight time, max coverage per day in kilometers, that kind of thing. You want to go ahead with that, Scott?
Yeah, so the payload, so it's a 6 kilogram sensor. It comes to just under 9 with the gimbal, which is required. So for our flight times, they vary. They very much vary, and that depends on the altitude, the area, everything. But we're only looking about 15 to 20, 25 minutes. 25 minutes is in absolute perfect conditions, and so coverage right now per day is about 1 kilometer squared. This is always a tough one because there's a big change happening. We don't want to talk about too much, but with a new type of system that's going to quadruple that. But as of right now, it's 1 kilometer squared a day. Looking at a solar window, looking at actually quite short solar windows. So depending on the terrain, we're looking at maybe a little bit more than that, and challenge days a little bit less. So right now, 1 kilometer squared a day. And as for the software, that would probably be a better one for Dean and Warren.
So some of the software is actually homegrown, and because we've been building and the homegrown aspects are building the automated processing for georectification through the atmospheric compensation, and we'll leverage third-party software where we need to. Specifically, we've leveraged Atcore and Parge, but that's really where it sits. The rest of it, the processing for L2 are algorithms that we've written, and there are our own variants of things. And then we also have our geocorrection process and automation that is completely on our own and that we've developed. Warren, what am I missing anything?
No, I mean, there is certain software tools that are specific to the sensor from high specs, and so we use that to do the sensor specific stuff, and then we take it once we get it to a fairly generic format. That's when our software comes into play and takes it from there.
On that note, just to expand a little bit on what Lori had asked. So yeah, for project sizes, just so you're aware, where we see the kind of the sweet spot is it's quite wide, but it's between 3 and 30 square kilometers. We understand for large regional exploration, this isn't the technology you go directly to. That's where you can go satellite or manned, and then we're more the scalpel for coming in. Right now, most of the projects that the largest project we're working on is 40 square kilometers, and the smallest one that we're working on is 3. So it gives you a bit of a range.
Well, that looks like we're pretty much it for questions. We're right on time there.
Lori's got another one.
Yep, there we go. Okay. So Dean Laurie asks, can you speak a little bit about the challenges of your orthorectification?
I don't think there's any challenges with it because I think we've solved it well enough. The real challenge in orthorectification is the collection of your GPS INS data and then having it really synced with it to your collection system. And fortunately, it's an integrated piece, but when you try to, the real challenge is not those pieces there, it's actually automating it, and we've solved that. So the most people, like if you follow some of the research that's out there, they're usually doing 1-2 lines and they're working at that aspect. We know from a couple ground checks that we've done, we're accurate easily within a meter of another known location from our RTK capabilities. And it's from an automated perspective of being able to push the data through, we're the orthorectification piece is not the challenge.
Yeah, and I mean, you may have noticed that in the data slides that we did present, we do have some data that shows erratic or holes in the display, and those, like Scott had mentioned as well, we want to show you real world data of what we've captured. So we run into issues in the field, and because or by being able to do in-field checking, which is something that we've really been working on a huge amount in these last few months, we've been able to really close a lot of those gaps and that kind of thing for upcoming future projects, that kind of thing. So. Mm-hmm. Alejandro asks, what's the maximum takeoff altitude and flight weather restrictions? So we can, with special preparation, operate at up to 5,000 meters above sea level. It's our typical loadout is for 3,000 meters or less, but we do have capability to set it up that way with our UAV system that we're using. And flight weather restrictions, ideally we're in that 6 to 8 meters per second wind or less. Always like less wind, but probably no more than 10 meters per second wind speed. And I should know off the top of my head what that is in kilometers or miles per hour, but I'm blanking at the moment here. Obviously, we wouldn't want to be working in wet, like in precipitation or anything like that. And also, we have to be aware of what precipitation was, prior to us operating, because that will affect the reflectivity of what we're seeing on the ground. So, if it just rained an hour or two before, we may be wanting to wait until the sun has dried that off before we're trying to go and collect data over an area there.
In the other aspect, on the altitude, the max altitude above the ground is dependent upon what each country has, because there are slightly different restrictions.
Yeah.
But there is a maximum altitude. I think it's 400 meters. Warren,
we would typically be operating to get our target resolution anywhere from 100 meters to 200 meters above ground for our flight operations. So that would be, so the flight planning that we use takes into account the topography. That's part of the reason we capture high grade DSMs beforehand as part of our pre-survey, so that we can be as consistent as possible with our above ground capture. Okay, we're at 12 o'clock here, or whatever time locally. 1 hour, I guess we'll say. So we'll probably close it up from here.
Yeah, that sounds great. Well, thank you everyone for joining us. And as Warren mentioned, you will all get links to the video of this recording. And if you have any more questions, don't hesitate to ask. Just because the webinar is over doesn't mean that we're not here to answer your questions anymore. So feel free to reach out to myself or Dean or both, and we will get back to you. But thank you everyone for your time today.
Thank you so much, Scott King.
Thank you.
Welcome.
Thank you everyone.